Hello students, welcome back to this lecture on the dynamic circuit families. Uh, so here I have drawn different types of combinational gates. One is the two input NAND gate and another one is the two input NOR gate. On the other side I have drawn the two input NOR gates. So this is the NAND and this is the NOR. And here in the individual parts or the individual components, I've got the unfooted ones and then the footed ones. Again, similarly, unfooted and footed NOR gates have been shown. The schematic of that is shown. So let's go over one by one. Two input NAND gates for an unfooted dynamic circuit will be is shown here with a clock PMOS transistor and the size of 1 here, and then the A and B transistors A and B inputs are connected to the NMOS transistors here with a size of 2. There is no foot gate or there is no foot transistor. So my logical effort for going down will be nothing but 2 and this one will see a benchmark inverter of 2:1. So my logical effort will be 2 for the input capacitance here divided by the 2:1 inverter will give me an input capacitance of 3. Parasitics will be nothing but 2 plus 1 here. The output node sees a capacitance of 3 and then divided by the 2:1 inverter's capacitance of 3. So the parasitics will be nothing but 1. If I look into the logical effort for the going down and compare with that of the regular CMOS family or the regular CMOS structure to input NAND gate, it turns out to be, we have the logical effort is nothing but 4 by 3, which is much greater than this 2 by 3. So this 2 by 3 turns out to be better one, right? And then the parasitics for the 2 input NAND gate was actually 2 in a regular CMOS structure 2 input NAND gates. Here it is actually 1. So again, a very beneficial and much more faster circuits. But if there is a contention here, the unfooted one always has a probability of getting contention between the pull up and the pull down circuit. So for example, if phi is equal to 0 during the pre-charge mode, this PMOS will be on, and for some reason A and B will be 1, so then my NMOS will also be on. So I will have a current on the pull down side, I will have a current on the pull up side, thereby that contention will be there, and that is the reason why we have a foot transistor, right? So now the foot transistor is there, which is the transistor closer to the ground rail, and whenever the phi is equal to 0, this will be off, so that contention or the path to the ground by the pull down circuit will not be complete, because even in a when phi is equal to 0, the pre-charge mode, this transistors will be off, and that's the reason why the discharge path is cut off. So the output can only charge to VDD, right? So it eliminates the contention problem, but because it adds the transistor, my width has to be different now. It has to be a size of 3 and 3 and 3, and thereby my logical effort and then the parasitics will go up, right? So the logical effort here for if I consider the input A here, the logical effort will be the capacitance of 3 divided by the benchmark inverter of 2:1. So it sees a capacitance of 3, so it is nothing but 1. Still better than the 4 by 3 the regular CMOS structure to input NAND gates. The parasitics now will be nothing but 1 plus 3 here, seen at the output node, divided by 3, so it is 4 by 3. Again, much less than that of the value of 2, what we had seen for a regular CMOS structure to input NAND gate. 2 input NOR gate, again on an unfooted side, I will have one PMOS transistor, which is nothing but connected to the clock signal, and then the A and B inputs connected to the individual branches NMOS transistors. So for an unfooted one, the logical effort will be nothing but 1 divided by 3. So 1 by 3, very less than that of the 5 by 3 what we had seen, right, for a regular CMOS structured 2 input NOR gate. And the parasitics will be nothing but 1 plus 1 plus 1, that is 3, the output node capacitance divided by 3, which will be nothing but gives me a value of 1. Again, the CMOS structured 2 input NOR gate is nothing but gives a parasitics of 2, whereas here the dynamic logic families gives a parasitics of 1. On the footed side, just to avoid the contention, we have one more transistor here, the foot transistor with a size of 2. And A and B transistors on the pull down side has a size of 2 and 2, right? So overall, the switching resistance will be nothing but R, because if either one of them is 1, the output will be discharged to ground, right? In the evaluation phase. In the evaluation phase means when the phi is equal to 1, right? So for the footed 2-input NOR gate, the logical effort will be different than that of the unfooted one, because there is an addition of one more foot transistor. So the logical effort, will be nothing but the input capacitance of either of these inputs will be nothing but 2 divided by the benchmark inverter's input capacitance, which will be 3. Again, it is much better than that of the 5/3 which we had seen earlier. And the parasitics will be nothing but 2 plus 2 plus 1, which will be 5, and 5/3. Right. So the parasitics seen by the regular CMOS structure 2-input NOR gate is 2. So this 5/3 is also better than that of the parasitics of the regular 2-input NOR gate. So note that the logical effort for the 2-input NOR gates or an n-input NOR gate remains independent of the number of inputs. Right. So the logical effort is actually dependent on the, we consider one of the inputs. So it really doesn't depend on how many number of the inputs are there, and so the logical effort for the NOR gate, in that sense, it doesn't really depend on the number of the inputs. Whereas for a NAND gate, if I keep on adding more transistors, because to accommodate more inputs, the sizes of the transistor sizes will change, and thereby the input capacitance seen will be changed, and thereby the logical effort will change. Whereas in a 2-input NOR gate, that is not the case. The logical effort remains independent. All right. Hope this is clear. Moving ahead. So there is one big disadvantage with the dynamic logic families, and that is what is stated here. So let's take an example of a dynamic inverter followed by another dynamic inverter. So what we really want is an input A. Whatever is the input A, either 0 or 1, the X will be the complement of that, and Y will again be the complement of X, and thereby I should see an output of the Y to be similar to the input of A, at least during the evaluation phase, right? Because in the evaluation phase, that is where the computation happens. That is when the the output is being evaluated. So I should get in the evaluation phase, I should expect X to be a complement of Y, and then Y should be a complement of X. Okay, so let's take a very simple case, A being high, right? So A being high, what we expect is X will go down to 0, and then Y will rise up from 0 to 1, and that's why I should expect Y to be very similar to that of the A during the evaluation phase. Let's say that the phi is 0 and then it goes to the evaluation phase. So phi is 0 and then it goes to 1. So when phi is equal to 0, X is anyways charged to VDD. Y will also be charged to VDD, right? So X, when phi is equal to 0, I will say that X has reached 1, Y has reached 1. So what it means is X is pre-charged to VDD and Y is pre-charged to VDD, or logic level 1, right? So when phi is equal to 0, X is high and Y is equal to high, right? Now let's say that when phi goes to 1, that is when this particular graph, when phi is equal to 1, all right, this is where the evaluation happens, and this particular phase is called the evaluation phase. Because A is high always, X will go down. A is high and phi is equal to high. So this will be on, and then this will be on, and X will now, and then of course this will be right. So what happens is when phi is equal to 1, this will be off, and then this will be on, and then this is phi is equal to 1. So this particular transistor, the foot transistor, will also be on, and then the X will go to 0, right? So that's what I've drawn here. The X will go to 0. But there will be some kind of a delay for X to go to 0, and that's what I've drawn in this particular transient graph. So I have an X value which will go to 0. So it stays high and then it goes to 0, and that is what I've drawn in the blue line here, indicating that the moment phi goes to high, the X will take some time, some non-zero time, and then it will go to 0, right? And then it continues to stay at 0 till the evaluation phase is there. Because that is when the A is continuously high during the evaluation phase, and that's why the X stays at 0. And then during the pre-charge mode, this particular thing, we'll call it as a pre-charge. And when phi is equal to the phi is equal to 1, this one we can call it as the evaluation phase, right? So in the pre-charge mode, the X will come back to 1 again with some kind of a delay, right? So the delay representation in this particular timing graph I have represented in the form of an arrows, right? The blue arrows for the X output. Now X goes to 0. What really happens to Y, right? Y, when phi is equal to 0, the Y has been pre-charged to 1, right? So the Y has been pre-charged to 1, right? So this particular portion. But the moment phi is equal to 1, so that means phi is equal to 1 represents this is on, all right? And X is still high in this particular case. So if I consider this particular portion of X, it is still high, right? So X stays high for some time and then it goes to 0, right? Because of the delay for the X to discharge, right? In this particular case. So X stays high for some time and then it goes to 0. So during that particular portion when X is equal to high, right? So this transistor will be on and Y is going to discharge now as well. So Y actually discharges to 0, right? The moment X hits 0, Y was supposed to go high because that's what we expect. But once the Y is completely discharged and then this particular transistor is off, right, during the evaluation phase, there is no path for Y to go to VDD or go to the logic level high, right? Because this transistor is off during the phi is equal to 1 during the evaluation phase. So Y doesn't have any path for charging and it has completely discharged because it sees X for a small duration, the X is high, right? So I've drawn this dotted line representing that the dotted line is our expected profile. But what really happens is once the Y comes down, there is no charging path. So Y stays at 0. So the Y output doesn't rise for the falling X input. So whenever the X falls, so during this particular falling X, the Y doesn't rise. So this is the real problem for the dynamic logic or the dynamic circuits. So what I've said here is for a monotonically rising input, it is required. The dynamic circuit works only for the monotonically rising input. So, here in this case for X, if it had been the opposite case, X was low and then it would have gone high, then the Y would have worked very well. So that then the Y was, it will stay at the logic level or it would have come down to 0, right? Because coming down to 0, it just depends on this particular X input. And phi is anyways 1, so it can easily come down, right? So it works for the monotonically rising input. It works only for the rising input. It doesn't work for the input going from high to low, right? So if the input is high for some duration and then it goes low, so during this particular duration, when it is high, almost all the dynamic logic circuit families, it will go to 0. And once it hits 0, it doesn't know how to come back to 1, right? So for a transition from high to low in the evaluation mode, it doesn't work, right? So it always needs a monotonic output, monotonic input, and that should be a rising input. So low in the evaluation phase, and then in the evaluation phase, it should go high. It doesn't work the opposite way, right? Very big disadvantage for this particular circuit. So that's why another family of the circuit has been deduced. That's called as a dynamic domino logic. Domino logic, it is basically coming. It's nothing but one can see that as a representation of both, a kind of a mixed bag. The dynamic logic family, and in between there is the regular CMOS family structure. So this is my dynamic circuit family, and then this is the regular CMOS family circuit. So it is basically a mix of both, and that is how the domino logic is formed. Right. So in this particular case, you have seen that these are the two dynamic logic, in fact, two dynamic inverter circuits, and in between, the regular inverter is being inserted. Right. So what this particular regular inverter does is, whenever the input goes from high to low or low to high, right, so W, we will get the output. This output is fed to the regular inverter structure. So the regular inverter structure doesn't really depend on the evaluation phase or the pre-charge phase. It just does, it gives me the output, which is a complement of that of the W input, right? So in our previous case, when X was actually going down in the evaluation phase, Y was not able to come up, right? So that is the case we are talking about. So in this particular case, when W, so let me pick up a color, when W goes low in the evaluation phase, right? So in the evaluation phase, so what I'm going to do is I'm going to draw the evaluation phase. So this is my evaluation phase, and right, and then the W goes low. It will take some time to go low, right? And during this particular phase, X output will take its own time, of course, and then it will be an inverted output. So I will have a rising output. Now this rising output is given to the next stage of the dynamic inverter, and rising stage is, rising input is not at all a problem for the dynamic inverter. Only the falling output is a problem. The rising output is not at all a problem. So in this particular case, Y signal, right? Y signal, it is pre-charged. It is completely pre-charged. And then whenever the X stays at low, it is Y will be connected to the VDD level, and then it is going to go low. So this will be my output of the Y. And then finally, Z will be nothing but, it's a regular inverter again. So I will get low, and then it is going high. So what we are doing here is adding an inverter to ensure that we always give a rising input to the dynamic inverter in this case, or for any other dynamic logic circuits. So the inverter is added to feed always a rising input. So the falling input is completely it's completely changed to a rising input by adding this particular inverter. And that's why it is called as the domino logic, because it contains both the dynamic logic as well as the regular inverter. All right. Hope this is clear. So that's what I've drawn here, the timing graph where A input is high. It is the similar one, very, very similar to that of what we had seen for the dynamic logic. Only thing is now I will have four additional signals, W, X, Y, and Z, which is nothing but the output coming from the first dynamic inverter, and then the second inverter, and then the third stage dynamic inverter, and then the fourth stage inverter. So I will have a pre-charge. So pre-charge will ensure that W is pre-charged to VDD, and Y is pre-charged to VDD, and X and Z are nothing but the inverted outputs of W and Y respectively, right? In the evaluation phase, W goes down because input A is high, so it goes down with some delay. X will will ensure that it goes high whenever the W goes low. Y on the other hand, because X is a rising input, Y will stay to VDD, and whenever it goes high, it will drop to 0 again in the evaluation mode, and Z will be nothing but the complement of the Y input, right? And note that here once the evaluation phase is complete, right, once the evaluation phase is complete, W comes back to 1 at the same time as that of the Y comes back to 1, right? Because so the evaluation is fed parallelly, or rather sequentially. The evaluation happens sequentially, but the pre-charge is done at the same time. So the pre-charge for all the dynamic circuits will be done at the same time because the clock is the same, right? So I've written here the pre-charge is actually parallel, and then the evaluation is kind of sequential. So the evaluation sequential means based on A, W will go down, and X will go high after some delay of W. after some delay, and then y will go down after some delay. The moment the x goes high, after some delay, y will go down, and z will go down after some delay from the y going down. So in that sense, it is kind of very staggered or sequential in the computation. But the pre-charge, that means that the w and then the y output goes high simultaneously or in parallel. All right. The one another aspect about the dynamic inverter, it is called as the dynamic inverter. It is not called as a static inverter. The reason is, it is dynamic in the sense that the clock is given to the PMOS transistor, and the evaluation or the computation happens onto the NMOS side. So that in that sense, it is called as a dynamic the inverter, and not a regular inverter or not a regular CMOS structured family of logic. Right? Hope you have understood this particular concept of starting with ganged CMOS family, where we saw 2 input NOR gates, and then followed by the dynamic logic families, and then finally we have arrived at the domino logic, which prevents that problem of the dynamic inverters, where the falling output is a problem for the dynamic logic families, and thereby the falling output is converted into a rising output. Note here that the domino logic is also applicable only for for a non-inverting logic. It doesn't work for the inverting logic. So we always need even number of stages, right? So the inverter is added in between. So we always have the even number of stages. And in this particular example, we have seen for the non-inverting logic. So it doesn't work for the inverting logic. So that is another disadvantage. But it avoids or eliminates that problem of the monotonically the falling input, right? So it converts that falling input into a rising input.